All right, so. Okay, so if you remember from last week, I think probably all of us, I did too. I got a warning saying, this variable new race is uninitialized, which it's just a warning. So the code still ran and it still created, our new variable called new race. So I fiddled around with R and Googled a bit too. So one way to get around this is, well, not really to resolve it, really, not get around it, is to first create new race. So sorry, ignore that comment. So I'm now first creating the new variable, and then I'm going on and recoding it. And so I'm guessing like this doesn't apply to when we did use that cut function to categorize our numeric variable. We didn't get that warning message. But for this, where it's like in base SAS, I guess, I'm sorry, base R, I guess R is a bit finicky, and so it wants us to create the variable first. So I've added that to the example code for exercise 1. So when I post the rest of the code for the rest of exercise 1, you'll see that in there now. But I just wanted to point that out. And then the other thing was, if you remember, we also generated a table 1. And so I've also added this line of code where you can output that table, because it just shows up in your console. And if you do try to copy and paste it into Word, it looks pretty awful. So you can actually output this table into a Word document using this function. And then wherever your working directory is, it will save it to here, or you can specify the exact path name, and then it will save to that subfolder that you've specified. So I've also added this line of code, and then that way, as you're working through exercise 1 to complete it, you'll have a nice table that you can attach to your assignment. So, okay, so just a quick recap. All right, so we talked about in the pre-recorded lecture about linear correlation, and the statistic to measure this is Pearson's correlation coefficient, and it's denoted by a lowercase r, and that just quantifies the relationship between two quantitative variables, right? So up until this point, we've really talked about just characterizing a single variable, and now we're talking about bivariate relationships, so the relationship between two variables. Pearson's correlation coefficient ranges from -1 to +1, with 0 meaning there's no correlation or no relationship. And so remember, the value of R only reflects the linear nature of the relationship. So if you saw in the different graphs, I gave examples where two variables could be correlated, but it's a curvilinear relationship. And so there are different statistics to measure that. For Pearson's correlation coefficient, we're just talking about a linear relationship. Even if a correlation coefficient is strong, we cannot infer a causal relationship. So even if the correlation coefficient is -1, which is the highest magnitude in the negative direction, or +1, the highest magnitude in the positive direction, we still cannot say that one variable causes the other. There are special models for that. We can only say that the linear relationship is strong, and then in what direction. So whether it's negative or positive. The other thing with correlation is we're just looking at the relationship between two variables, and there may be other variables other than X that influence the value of Y. And I think most of you have either taken an EPI class or are taking EPI. And so in EPI, you'll start to talk about confounders or mediators. But typically, when we're looking at a relationship between two variables, almost always there's other factors that might be influencing that relationship that we might need to consider. One limitation of the correlation coefficient is that it can be easily disrupted by outliers, right? So when we fitted our best line, if we have an outlier sort of pulling that best fit line towards it, that can change our correlation coefficient. And if we were to remove that outlier, then it would probably fit better with the rest of the data points. If we square Pearson's correlation coefficient, we get what is known as the coefficient of determination. And that's just, for in this case, lowercase r squared, and that ranges from 0 to 1. And that just measures the proportion or the amount of variability in one variable that can be explained through its relationship with the other variable. And we'll talk more about it in a future lecture about non-parametric methods. But if our distribution, if our variables are not normally distributed and a linear correlation, so Pearson's correlation coefficient is not appropriate, then there are these non-parametric correlation coefficients. So Spearman's rho is one of them. And these are all just sort of based on ranked data. So we would take our data points and for each variable and we would rank them. And so we were not, in this case, we're not looking at the actual values, we're actually comparing the ranking of the two values. And that's the same thing for Kendall's tau as well. Spearman's rho is more commonly utilized. You'll probably see it way more than Kendall's tau, but Kendall's tau is more robust. So it performs well even if you have a small sample or you have outliers. Okay, and then we had this tie-in with regression where correlation is really just the same thing as regression in its simplest form. So when we're conducting a linear regression and we're just looking at a single variable, we typically call it, so X would be our predictor or our independent variable, and its relationship with Y, or our outcome or dependent variable, that is called simple regression. And it is the same thing as correlation when we're just looking at those two variables. And so the regression line is just a statistical technique for finding the best fitting line, right? So sort of intuitively, when we see a scatter plot, we want to see a line that sort of cuts through the middle of all the data points. So like this, the figure on the left, right? Whereas the figure on the right, we know visually, we can look at that and say that's probably not a line that fits the data points very well. And then the regression line just minimizes the error in predicting a line that best fits the current set of data. Okay, and then, so I introduced this equation, and it's really just the application of the linear equation. So something that most of you have probably seen in high school, right? The y equals mx plus c. So it's just the same form. And then again, x is our predictor variable and y is our outcome variable. And then I think I won't spend too much more time on the notation for this. Really the takeaway is that the regression line really is just an application of the linear equation. So it has a y-intercept and the slope. And it's really just trying to minimize the error, or fit the best line by minimizing the error between the predicted line and the actual data points. And that's true even if we were to add additional variables to look at. So if we had more than just one independent variable. So let's say we wanted to look at age, we wanted to look at sex, and we wanted to look at BMI. So we had 3 X variables. It would still be the case where regression is trying to fit a line and fit it best to our data. Okay. And then I don't think I had a slide like this in the pre-recorded lecture, but I'm putting it here now. If we want to interpret our model as results, how would we do that? So here we have our estimated y, and then we have a coefficient, a beta coefficient, so our b value, b hat sub 1 is negative 8.94. And then our y-intercept is 125.96. So if you remember in the example that I gave in the pre-recorded lecture, we were looking at this number of sleep hours. In this case, it's looking at the author's sleep hours and her grumpiness level. So how would we interpret this intercept? So remember, if x is 0, so in other words, if she's getting no sleep, then this term cancels out, and we just have the value 125.96, and that would be her grumpiness points, and that would be somewhere up here. And then we interpret the slope, remember, just like we would with a linear equation, if x increases by 1 unit, this is the value by which y changes. And in this case, it decreases by 8.94 points. So for every 1 hour of sleep, additional hour of sleep that the author gets, her grumpiness points decreases by 8.94 points. And then just a note, when we output model results, it will give us a capital R squared, and we can use that to assess model fit. And for simple regression, the capital R squared is the same as our coefficient of determination. Okay, and remember we had a few assumptions for fitting linear models. The first is that the observations are independent of each other. And this is the exception is if we have repeated measures. And I think now I'm seeing as I talk to some of you, I think most of your research will probably involve repeated measures. We also assume that the residuals, remember that's the error between if we were to fit a predicted line here and look at the difference between the line and the actual data point, that's called the residual. So we assume that the residuals are normally distributed. And then finally, we assume that the data points vary evenly. So this is a case where those data points would vary evenly. And then you see here, this is an example of where they don't, because they're spread out here. And so there's more variation up in this area versus here for these values of X. Okay, and then at the end of the lecture, we talked about t-tests. We had a 1 sample t-test, and then we had 2 sample t-tests, the first being an independent t-test where we have independent samples, and then the second 2 sample t-test where we have dependent samples or paired data, in which case we talked about a paired t-test. Okay, so remember when we're estimating the population standard deviation, it's biased, right? So we had to make that adjustment and use the estimated population standard deviation instead of the actual population standard deviation, because we don't know that. So when we make that adjustment, we end up using a t-distribution because of the potential error in our estimation. And this is just this is the article, and it's published by William Gossett. He worked for Guinness at the time, and he was not allowed to, he basically characterized the t-distribution, but I guess the employees weren't allowed to publish under their actual name. And so he just published it under the pseudonym student. And so the t-test is also known as student's t-test. The t-distribution shares many of the same properties as our standard normal curve or the z-distribution. The difference is the z-distribution assumes that we know the population standard deviation. And for a t-distribution, the tails are heavier or fatter, so they contain more extreme values on the left and the right. And this is especially true for smaller samples. And so I think in the pre-recorded lecture, I showed a graph where you could see the Z distribution, and then you could see the T distribution for increasing sample size. And so when we get to a very large sample size, it starts to look a lot like the Z distribution. So this is just a recap of the different t-tests that we talked about in the lecture. So the 1 sample t-test, so we have a known population value. So we might set it to 0. We might set it to, in the textbook example, the author took a sample of psychology students from a larger class of psychology students. And so she knew the average exam score in the larger class. And so she was comparing in her sample of the psychology students, their exam scores, so their mean exam scores compared to the larger class. And in this case, the mean exam scores for the larger class was the population value. If we have 2 samples, and in this case, if we have 2 independent samples, then our null hypothesis is just Oh, I'm sorry. This is an error in my copy and paste. So this should be mu1 and mu2, where the population mean in group 1 is equal to the population mean in group 2. So I'll go ahead and correct this before I post the PDFs. So I apologize for that. And then for the two sample dependent t-test, now we're looking at the difference between the means. So our null hypothesis is that the difference in the means is equal to 0. Whereas in these, the one sample and the independent t-test, our assumption is that the scores are normally distributed. So the scores making up the mean for these two groups, or the mean for our single group that we're comparing to the population value, we're assuming those are normally distributed. But in the dependent t-test, we're assuming that the difference in the means is normally distributed. When assumptions are not met for the t-test, so when we don't have normally distributed data, then we would use the Wilcoxon signed rank test. And this is an alternative to the one sample t-test or the paired t-test, or we would use the Mann-Whitney U-test, and that's the non-parametric alternative to the t-test for independent groups. Okay, so that's all I had for that. And now, so I guess I'll just ask, does anyone have any questions about that? Let me check the time. Okay. If not, let's go ahead and open up our studio. I'm going to open up ours on my end as well. Let me just switch over. Okay. Okay, does everyone have R open? Do you need a little bit more time? Okay. Okay, awesome. Okay, turns out I need.
How do we get it back to like how it looked when we were working on it?
Oh,
because I just have like the console. Oh, I think I put new script, right?
Oh yeah. So go to File and then go to Open File. And then if I were to click on Open File, it will open up, this is the last folder I was in. So, but you might, you'll see another folder. So then just go ahead and navigate to wherever you've saved your code for exercise 1. All set? Okay, so I'm going to scroll down to, and everyone was okay with the code for assessing normality. So basically you had everything here for all of the different variables. And then in my example code, I basically just put age and you would just repeat it for all of the other variables, except for the categorical variables, right? Those aren't going to be normally distributed.
I don't know about anybody else, but I had trouble installing the package that ggpub-r.
Oh, okay.
Every time I would go to run it, like when I would do like library and then ggpub-r, it says loading required package ggplot2.
Oh, okay. So I think it's because this is a package within that package.
Okay, so then I downloaded that one.
Okay.
And I ran it.
Okay.
and then I did the like the GG density, all that, like that code.
Uh-huh.
And then it said like it couldn't identify like GG
Okay, so
density.
your package actually wasn't installed. Okay, so
Yeah.
let's go to tools
Okay.
and let's do it this way, like without code and just do it with the drop-down menu. Go to tools and install packages. My internet's like slow today. Okay, and then I'm actually gonna write in ggpubr. So go ahead and select that one
Okay.
and then install it. And I might just say, okay, so it's installing now. Okay, so now has, so the package has been installed to my hard drive.
Yeah.
And then I'm going to highlight library ggpubr and hit Control Enter just to run that line of code. It should, I'm just crossing my fingers now. Okay. So let me see if that actually works. I'm gonna load, go up to, sorry, I'm just scrolling up to load the actual data set. Okay. And then just see if this works. Let's see. Okay, so it does work for me.
Okay. I just got it.
Okay, awesome.
Yeah. Thank you.
Okay, so these are all for question 2, and then for the outliers, sorry, I'm probably making you guys nauseous scrolling up and down. This is code that you'll want to expand on to look at the rest of your outliers or rest of your variables to see if you have outliers. And then again, that's just for your quantitative variables. You don't have to do that for like race, ethnicity, for example, or for gender, or anything like that, since those are categorical. Okay, so question 4 in exercise 1 asks if grip strength and explosive power are correlated, and those are both quantitative variables. And so the way that we want to assess whether they're correlated first is to put together a scatter plot. So we can do that with this code, and I'm gonna copy and paste that into the chat so that you guys can just copy and paste it into your R script. And if I run that, I get a scatter plot. Okay, and then I put like a note to myself to remind myself to tell you guys that I can copy and paste this. So you can just right click on it and copy image and then paste that into a Word document. So that's what you would do. You would just copy and paste this into your Word document with the exercise questions, and then that would be sufficient for your scatter plot. Okay, and then
I haven't gotten it yet in the chat.
Oh, everyone. Oh, sorry. I sent it to everyone there. Okay. I was still set to everyone in the waiting room, which is nobody right now. So there, that should be it. Okay, so what this function is doing is it is telling it this is our first variable, this is our X variable, right? And then my data set name is called physiology. And then this is our variable grip strength. And then it's specifying the Y variable, so the other variable, explosive power. And then I'm just giving it a title, and that title shows up here. And then I'm specifying what the X labels and the Y labels are. And then this is just the size. So if I were to increase it, these dots would be larger. If I were to decrease it, they would be smaller. And then the other thing I should note is just make sure you load your data set that you saved from last week. So just let me know. I don't want to move on until I know that everyone has successfully plotted their scatter plot.
Is it that tidyverse package from the library?
To load the data set.
I think I did something wrong.
Oh, it's okay. What error are you
I
getting?
think I'm also not, I haven't even loaded the data set either.
Okay, no problem. And that's my bad. Like I should have started with that actually. Okay, so I'm gonna copy and paste what I use to load my data set. What you'll do is after the file argument, you're going to want to change what I have in quotes to whatever path name you have. So for example, go to where, whatever working folder you're in. So in this case, this is my working folder for exercise 1. I've set this as my working directory. So now if I want to load the dataset physiology, that's in my datasets folder. So I put datasets here. Sorry, I put datasets here. And then if I were to click on datasets, you can see my physiology R data is in that folder and it's called physiology. So I put physiology.r data. And then you should be able to load it from there. I think if I write, okay.
Would you be able to copy and paste everything you have in let's see, on the top left quadrant 1, and then
Up here.
Yeah, because then at that point I could just do Control Enter and then have what you have.
Oh, did you not save your data set from last week?
I think I did, but it's still not, because I still have it up.
Oh, okay. So let me copy and paste that. You're going to want to change some of these. Or what you can do is copy and paste this code and then import the physiology data. So just click on, if you're able to, click on the Stata data set or SPSS data set, click on it, import data. For everybody else, if you saved your data set, you can actually just go to your R data set and click on it, and then it'll give you a pop-up message saying, do you want to load it? Yes, so the data set that I'm loading is the one that we pulled in the raw physiology data, and then remember we recoded and added like race variables. Yeah, so how would I do this? I'm going to post the R data set that I have, this physiology data set. I'm going to post that to Cougar Courses really quickly so that you guys can just save it to a folder and then load it from there. That way you don't have to rerun all of this code. Does that sound good? So let me go ahead and do that. Okay, so I'm going to post this in the exercises section of the website. So Okay, so it's on Cougar Courses now. So if you go to Cougar Courses, go to exercises, that second section, click on it, and you should see the third file that I've added under exercise 1 is the physiology data set. It's the R data set. Just right click that and then save it to, save link as wherever, your working directory is. So wherever your folder is for R. And then let me know when you guys are ready. Let's see.
So it's under exercise 1, and then there's the physiology data set, SAV and CSV.
Yeah,
Which
so
one?
right click on it should show the third, there should be a third one where it says modified physiology data set, R data. Does that show up? Let me just double check.
Yeah, I see it now.
Okay, perfect. So right click on that and then just save it to whatever folder you're working from for exercise 1. Oh, I wonder if I can. I'm going to drop it in the chat too. I'm not sure how it works, like saving a file from the chat, but let me just try and see if that's helpful as well. Okay.
I have it with it as the Excel sheet on my top left console.
Oh, up here?
In the quadrant 1. I keep forgetting what it's called. The top
Here?
left.
Oh, here.
Yeah.
Oh. So you should see a tab here with the data and you can just like click it. So if I were to do that too, if I were to like do this, you can see the data. And this is the data set we created last week, right? So we have the new race, we have like the new height variable, the BMI categories and BMI. You can just see this little X here. Go ahead and click that and that'll close that out. You can also toggle between tabs, kind of like you do on a browser,
Right.
where you have multiple tabs. So you can do that too if you want to keep it open. So, okay. Once you have the R data, you should see it in your folder here. So this is my, my working folder is exercise 1, and then I have a separate folder for data sets. Once you see that, you can actually just click on it. And then you should see this window pop up. So let me know when you have your data all set. Okay, awesome. Does anyone else?
Mine just has like the loading circle has been going on for a while.
Yeah, mine just says load and then nothing's happened.
Okay.
Maybe I just have to be patient, but
So does it just say
that was happening with mine, but then I was still able to plot.
Okay, so if you were to run this code that I'm highlighting here, so instead of like clicking on it and loading it, if you were to just run this code, to load it, once it's loaded, it'll be blank. So if I were to like clean this up and like load that, it's already loaded. But if I just do that, that's all I'm going to see. I'm not going to see any messages or anything like that. But if I were to write physiology, it should show up. Do you see your data appear? For those who who tried to load it and then don't see anything else, do you see your data up here in the upper right corner?
No.
yeah, mine's up there.
Yours is up there. Okay.
Mine is not showing up there, and I still just have the little loading circle. And I tried just running the plot just to see if it would go anyways, but
yeah.
nothing happened with that either.
Okay, so I'm going to suggest maybe just closing R Studio. Don't save your workspace. When you open it back up, just go to your directory where you've saved the R data set and then load it from there and just see if that works. It might be more, it might be like a network thing and not so much an R thing or anything that you've done. Okay. So we'll give it a sec so that Amanda, we'll make sure that you have the data set loaded. Otherwise, the rest of this is going to be pretty useless to you.
That worked.
Okay, awesome. I'm going to delete that. Okay, so now that your data set is loaded, you might have to reload some of these packages. So let's just see. I think plot is in base R, so it should still work. Okay, so here we have our scatter plot. Let me recopy and paste that code for you guys, and then just see if that works for you. Will it show up in R Studio? You did save it. Okay, so Alex, if you use the use this area down here, the directory, sorry, I can't think of the name, to find the folder where your R data is, you can click on your R data set, so wherever you saved it, and then once you do that, R will give you a pop-up message asking if you want to load the R data, and then you'll just click yes. Okay, and then again, that R data set is different than the CSV and the .save file. The R data set has the variables that we created in last week's lecture. So Alex, let me know when you have that data set. And then everyone else, if you don't have your scatter plot, just send a note or say something.
I feel like I should probably just like verbally tell you this.
Oh, yeah.
So I've
Okay.
like, sorry,
Okay.
I saved the file and I did the right click thing. And usually when I do that, the thing will show up in that area you were referring to. But for some reason, I'm like looking everywhere and it's not there.
Oh, so it's not here.
I don't know what happened or where it went, but.
Oh, okay. It might be like in your downloads folder or, but I mean, if you want to try again, if you scroll up in the chat just a little bit, I've also posted the file there. So I think you can, let me see what happens if I click it. Sorry.
Wait, I think I might actually have it. I think I found it.
Okay, awesome.
Okay, I'll try it out now.
Okay, no problem. Does everyone else, are you able to see your scatter plot? Sorry, mine's like squished. I can expand it a little bit there.
I have one quick question.
Sure.
I've been able to load everything, but when I look at my data set, it says that I have 16 variables.
Interesting. And you loaded the R data set?
Yeah, I think so. It's hard to like remember exactly what I've done, but
hold on one second. It might just be because it's in this window, it's only showing you a subset of, that's really weird. Hold on one second.
It says I have 20 observations of 16 variables, but yours said 15. I just didn't know if that was like a big deal.
1, 2, 3. It shouldn't be, as long as you have all of the variables you need. That's really weird. But it's just
Okay.
bothering me because that's really weird. Because we're running, like, you pulled the exact data set.
Yours,
Okay, it's
let me see.
15. I still show 15 variables. That's really weird. Okay.
It says 13.
13. Oh, interesting.
I had this issue last time. I downloaded like the Excel one. I think.
Okay, and then worked through the code and then saved it?
Yeah.
Okay, so it might just be, I wonder if it might be where like I ran some other code after our class yesterday. No, I mean last week, sorry. That's really weird. Okay, I'm gonna have to like look into why that might be happening. If you run into a case where we're running some of this code and R gives you a message, an error message saying, it doesn't recognize a certain variable. So therefore, in your set of 13 variables, it doesn't include maybe the 14th and 15th are like BMI, for example, and the BMI categorical variable. Then what you can do is just go ahead and take the physiology R data that's on Cougar courses or in the chat and just save that one.
Yeah, I think mine might have, I don't know if we made a new height variable or if it just like I accidentally made one.
Yeah. Okay, so we did make a height variable that was binary, right? So it was just less than or equal to 69 inches or greater than. Does everyone see these new variables, new race, new height, BMI, and BMI cat?
Yeah. I have them.
Okay. Okay. All right. This is
I have an extra like X1, it says, just like random column.
Oh, okay. So it might just be because last week I did have, or I also had an example code I may have left in where, I'm giving you, for example, the function. And then instead of, for example, physiology $age, the example would have been like X, just to let you know, okay, put in your X variable. And so if you ran that, it would have created that variable in your data set. So, don't worry about it. It's an extra variable, but you're not going to use it. I'm going to maybe offline, if you want, send me a note. Sorry, I can't see who's actually speaking. Who only had 13 variables in their data set?
Me, Peter.
Okay, Peter, sorry. Sorry, I just see my R console, so I can't see when you guys are actually like who's speaking. So Peter, if you run into issues, or actually if you want, you can email me the data set that you saved and I can look at it and compare it with the data set that I have, because it's kind of bothering me that you don't have all of the variables you need. So I kind of want to figure out why that happened. And then that way I can relay that back to you. And then moving forward, you're working with the complete data set. So if you don't mind, emailing your data set with the 13 variables, and then I'll troubleshoot and then send you a note back, and hopefully, find a resolution to that.
Sounds good.
Okay, thank you. Okay, so everyone has their scatter plot now, right? Okay, awesome.
Yes.
Okay. So now what we're going to do is add a best fit line. So we're going to use two functions. So this LM function here, that stands for linear model. And we have, and you'll see this with a lot of functions. Your Y variable goes first. So in this case, it's explosive power, right? So that's our Y variable. And then there's a tilde here, and then we have our X variable, grip strength, right? So here's our X variable. And then we're just saying we want that line to be red. This argument corresponds to the function AB line, and that's just going to plot that line. So this function is finding the best fit line, and then the AB line is going to plot that line. So let me highlight that. I'm going to copy and paste it for you guys. Okay, and then I'll run it on my end, and you'll see. And this makes sense, right? So you can see my line. Hopefully you guys have a line too, where it's almost flat, which would correspond to a correlation of 0. And that makes sense, right? Because it doesn't look like explosive power and grip strength are very correlated at all. The data points are sort of all over the place. All right, so everyone sees their red line, right? Okay. We didn't talk about it in class, but this is an example code that maybe would be helpful for you in the future, and I'll just show you what happens. So this is a Loess curve, and it's a non-parametric smoothing technique. So when our data points are not linearly related, sometimes we can fit a Loess curve, and that just allows the data to be non-linear. So we talked about curvilinear relationships. I think in this case, there's probably just no relationship, but I just want to show you what that looks like. So I've pasted the code into the chat, and then I'm going to run it on my end too, and just show you what that looks like. So you can see it's this curvilinear relationship. Okay. All right, so is everyone good? Okay, so then the question also asks, which correlation would probably be better for this bivariate comparison between explosive power and grip strength? So what is the assumption for the Pearson correlation coefficient? And sorry, the question is asking, should we use Pearson's correlation coefficient or a non-parametric correlation measure? So like Spearman's rho or Kendall's tau. So I'm throwing that question out to the class. Based on what we've seen so far, what do you think?
Not Pearson's correlation.
Yes, totally. Right, because they don't appear to be linearly related. They really don't appear to be related at all, but let's just check the different correlation coefficients. Okay, so for Pearson's correlation, if we've met our assumptions, then this would be appropriate. So here again, we have our Y variable, explosive power. We have our X variable, grip strength. And then this is just telling the function core.test that we want to run Pearson's correlation. So I'm going to copy actually all 3 of these to the chat so you guys can run them and take a look at what that looks like. So then, okay, so what I'm doing here is I'm creating an object A that I can go back to, and you'll see what I mean by that. So A, I'm getting a Pearson's correlation coefficient. For B, I'm running a Spearman's rho, and then C, I'm running a test on Kendall's tau. So I can actually run all 3 of these. Okay, you'll probably get these warning messages as well. It's just saying that the test can't compute an exact p-value because we have ties in our data. So remember, for the non-parametric, so I'm just highlighting what I'm referring to. So if you look in my console here, under Spearman's correlation, I have ties. So when it's ranked the data, there must be, for example, 1 through 20, it's going to rank grip strength 1 through 20, explosive power 1 through 20, instead of the actual scores for those variables. And then it's going to look at the correlation between those rankings. And then it just looks like there's probably ties in our data. So that just means that two data points in one of these variables or more are equivalent to each other. And so when they rank it, I might end up with something like 1, 2, 2, 4, 5, 6. And it's just saying I can't compute an exact p-value if I have ties, but it will still calculate the p-value associated with the test. So you can ignore those warning messages. Okay, so now that you've run those 3 lines of code, I'm going to go down here to the console and just type in A, and you'll see the result of our test for the Pearson's correlation. Okay, so it's showing you the data that we used to run it. This is our t statistic. So that's the value of our t statistic that we would be comparing to critical values. We don't do that anymore because we have computers now. But before we had something like this, we would calculate our t statistic, and then we would open up a book. And in this case, for the t distribution, it's like a ginormous book because the t distribution differs depending on the sample size. And then we would compare it to a critical value depending on the degrees of freedom. And in this case, the degrees of freedom is 18, right? So when we run a t-test, we're looking at pairs instead of like singular values. And so the degrees of freedom is actually our sample size minus 2. And then here we have our p-value. Okay, so the p-value is 0.8448. So what do we do? Remember, our null hypothesis is that correlation is 0, and our alternative hypothesis is that the correlation is not equal to 0. So with a p-value of 0.8448, what conclusion do we make?
Do we reject the null hypothesis?
So
Fail to reject?
We actually fail to reject the null hypothesis. So remember, if the p-value, and remember it's an arbitrary cutoff, but it's the most common one, is less than 0.05, then we reject the null hypothesis in favor of the alternative. But in this case, it's greater than 0.05, so we fail to reject it. So we fail to reject the null hypothesis that the correlation is equal to 0. Which makes sense, right? Because if we look here, it really does look like there's no correlation at all. And then in fact, when correlation is estimated from the sample, it's very close to 0. And you can see here it's 0.0467. Okay, awesome. So now I'm going to look at the output for Spearman's row. So I'm going to type B into the console. Okay, and then here's the output, and it looks very similar. In this case, the statistic looks like it's an S statistic, and our p-value is 0.8048. So again, because it's greater than 0.05, we fail to reject the null hypothesis that the true row is equal to 0. And then now, so this is great because it's pretty consistent whether we run the Pearson's correlation, which we shouldn't anyway, because the data don't meet our assumptions of the tests. But when we run these non-parametric tests, we get similar results. So now if we look at Kendall's tau, so maybe it's more information and hopefully it's not confusing, but Spearman's row is kind of like an extension of it. Mathematically, it's trying to sort of look a lot like Pearson's correlation coefficient, whereas Kendall's tau is mathematically trying to go back to like approximate a z distribution. So it has this z statistic here, but it's a non-parametric test. And then again, you see our p-value is greater than 0.05. It's 0.7936. And so we fail to reject the null hypothesis that tau is equal to 0. So for this question, you would, we asked it earlier and we would say, okay, Pearson's correlation is really not the appropriate test. We would probably want to use Spearman's rho or Kendall's tau. It's a relatively, a size, usually, so a sample size of like 30, we would say, oh, that's large. So maybe in this case, we would want to use a Kendall's tau because it's less than 30, but either is really okay. And again, the most common non-parametric correlation you'll see is Spearman's rho. So you could run both or one or the other, and and I would say, yes, that's fine, as long as you decide not to use the Pearson's correlation coefficient. Okay. So let's move on to question 5. How's everybody doing? Are you guys feeling okay so far?
Yeah.
Okay. Okay, so question 5 asks, is there a difference in grip strength by gender? All right, so what can we do? We can first look at a histogram for grip strength. We can look at the, so I think this plots the density. No, sorry, a smooth curve. Okay, and then we can look at actually test whether this is normally distributed, right? So this is just assessing the assumptions of the t-test. So I'm already like giving myself away here. So we're actually going to run a 2-sample t-test, right? So let me explain why. So grip strength is our quantitative variable, and now we're looking at whether grip strength differs by gender, so male, female. So we're looking at 2 groups, and those 2 groups are independent of each other, right? So we want to compare mean grip strength for men versus women. And so we can use an independent t-test. But before we do that, we want to make sure that grip strength meets our assumptions. Make sure that it's normally distributed, right? Before we go ahead and run a t-test, because if it's not normally distributed, then we might decide to use a non-parametric test to compare the 2 groups. So let's go ahead and run that. I'm going to copy and paste that code here. Okay, and I'm just going to run the first line. It looks kind of skewed, but we also only have a sample of 20 people. So let's kind of go on and see what this, oh, sorry. Oh, sorry. So this is the QQ plot. So remember, the QQ plot plots our data against a standard normal. And if our data points fall on that line, then we can say it's probably pretty close to normal. And it looks like for the most part they do, right? But now let's actually test it. So remember, if we want to test normality, one of the statistical tests that we can use is the Shapiro-Wilk test. So I'm just going to run that now. Okay. Okay, so this is the result for the Shapiro-Wilk normality test. Again, our variable is grip strength. This is our test statistic, and our p-value is 0.5922. So what would we conclude in this case? So remember, the null hypothesis is that the data are normally distributed. And then the alternative is that the data are not normally distributed. So with a p-value of 0.5922, what would we conclude here?
Not normally distributed.
So it's greater than 0.05, so we fail to reject the null hypothesis. So we would actually conclude that the data are normally distributed because we fail to reject the null hypothesis that they are normally distributed. then like, these are weird. This is actually like a weird null hypothesis. So I guess I know. Yeah. So I was just going to say like, that's why it's so confusing, because this is also just a weird, so normally like our null hypothesis is like, this is equal to 0, or this is equal to each other. And in this case, it's like, this is equal, it is normal. So yes, so it's definitely confusing. So what can be helpful is to actually write out on paper, okay, the null hypothesis is that the data are normally distributed. And then if it's greater than 0.05, I'm failing to reject that. So I accept the null hypothesis. So in this case, it's great. Our data are actually normally distributed, and it does look like it when we look at the QQ plot. It didn't really when we ran our histogram, but all signs point to grip strength is normally distributed, and so therefore the t-test is an appropriate test, and we can actually use it. Okay, so I put all these spaces here just to like pose the question to the class, but my scrolling was not great, so gave it away. Here, we're running a 2-sample t-test. Okay, and to do that, we use our function t.test, and I'm just going to paste that in here. Okay. So again, y comes first. So it's grip strength, and then so that's our dependent variable. And then gender, right? So we're comparing mean grip strength for men versus women. So gender is our independent variable, or our X variable. And then we're just specifying the data set. And then we're saying variance is equal. And that's to say that it's an independent t-test. So now we're going to highlight that and run it. So is everyone good so far? Okay.
Yep.
Okay, awesome. So here we have a p-value of 0.4834. And remember, our null hypothesis in this case is that mean 1 is equal to mean 2. So grip strength for men is equal to grip strength for women. So given this p-value, what would we conclude from our data? So it's greater than 0.05. So we would, again, fail to reject the null hypothesis that the means are equal. So we would say, okay, we fail to reject that they're equal. So we're accepting that the grip strength for men is equal to grip strength for women. There's no difference in our, at least using our sample, we would conclude that there is no difference in grip strength between men and women. The nice thing with the output for the t-test is it also gives us the actual mean value. So the mean value for grip strength for group 1, and that's the men, and the mean value for grip strength for group 2. And you can see they're pretty close to each other. If we had a large sample, maybe like 100 or 1,000 individuals with the same means, because the variability might be smaller for this larger sample, and because it's a larger sample, we might actually get a significant p-value, even with the same means. But in our sample of 20, we're failing to reject the null hypothesis that they are equal. And so then we conclude there are no differences in grip strength between men and women. Okay, so that's that for the physiology data set. And then the next set of questions actually pull in a different data set. That is also posted to Cougar Courses. So if you have not downloaded that data set, go ahead and do so now. And I can also post this file to the chat if you need me to. So let's see, let me just do that now. Okay. Okay. let me know when you're ready. Oh, so I'm actually going to pull in my, yes, it's a CSV file. You can click on it, save it where you need to. And then you can probably, if the easiest thing is, so you see here in my directory, I have it, you can just click on it and import the data set. But I'll also send you the code that I've used to pull that data set in. Okay, so let me know if you're not ready, and then we'll just give it a few more minutes.
I'm not ready yet.
Okay.
Okay, I think I'm good.
Okay, is everyone else okay?
Yeah.
Okay, awesome. Okay, so this data set, if you see on the exercise sheet, it gives you a data dictionary. It tells you there's a column for sprint times pre-supplement, and then there's a column for sprint times post-supplement. I think the version that you have shows that there's also a supplement variable, and that's just dichotomous, or binary, it's just 0 or 1. That variable is actually not in the data set. So in this particular data set that is posted to Cougar Courses, and I just sent through the chat, everybody in this data set took the supplement. So now what we're looking at is individuals who ran, they ran, and we're giving them, we measured their sprint time, and then they took a supplement. So everybody took a supplement, and then they, retested. And then now we're taking their sprint time for post supplement. So after they've taken the supplement. And then the first question that's being asked is, what are the mean sprint times for both groups? But again, this is all, everybody has taken the supplement. So now we're just looking at what are the mean sprint times pre-supplement, and then what are the mean sprint times post-supplement. And then if you remember from last week, we use this function called mean. And these are both quantitative variables, so we can go ahead and run the mean for those two variables. And then I'll copy and paste that as well. So if we look at the results here, before everyone took the supplement, it looked like the mean sprint time was 12.3, and I believe it's seconds. And then after the supplement, it was 12.0. So they look pretty similar, right? So far, based on our results, we don't have like a lot of confidence in the supplement. Then again, if this is a 100-meter sprint, which I'm guessing it is based on the times, that's actually a huge difference, right? So when we're talking about a 100-meter sprint, 0.3 seconds is a lot. But it looks like it's in a direction that's not, it's not preferable, right? It is preferable. It's faster.
I have a quick question.
Sure.
Just so I understand what I'm doing, when I type in mean and then the sprint times, I'm just telling it to look at the sprint time data, and then the $sign is then telling it to look at the subcategory pre-sprint times or the post-sprint times. Is that, understand that, right?
Yeah, so
Okay.
right, so sprint times
Cool.
is the data set, and then sprint times pre is the variable. So
Okay,
you
so
actually
that-
have, let me
Oh, sorry.
see.
Go for
Oh
it.
no, so you actually do have, let me open up the data set. So this is just the ID variable for those individuals, the 22 people in our data set. And then you can see there are two additional variables, pre and post.
Cool. So anytime I use that $sign, that's telling it to look at some sort of
The column.
column. Okay, cool.
Yeah,
Thank you.
And that's actually, I'm glad you asked that question, because sometimes you'll see data. So this is actually an example of a wide data set, right? So we have one row per person, and we're looking at time point 1 versus time point 2 in different columns of data. So this would be a wide data set. If the sprint times post, for example, if we had 2 rows per person, so person 1 had sprint time here for time point 1, and then they had a second row with their post supplement sprint time under this. So if it was row 1, it would look like 1, 11.8, and then row 2 for this person would be 1 for their ID, and then 11.3. That would be a long data set. And different functions actually prefer different data structures. So in this case, we have our wide data, and we're looking at the mean sprint times for those 2 pre and post supplement sprint times. Okay. So yeah, thank you for asking that. So now we want to know, is there a difference pre-supplement versus post-supplement? And then in this case, what type of test should we use? And this assumes that our data are normally distributed. So I'll say that we're meeting all of the assumptions. I'll give you a hint, we're running a t-test, but what kind of t-test should we run in this case?
Paired.
Exactly. So we're going to run a paired t-test in this instance because we're looking at pre and post supplement times in the same individuals. So we're looking at a within mean difference. So that's what we'll do. So again, what I'm looking at here is, so remember, for a paired t-test, we assume that the differences are normally distributed, not the sprint time pre-supplement and sprint time post-supplement. We're not saying that those 2 are normally distributed. We're saying that the differences are normally distributed. So what I've done here is first create a variable called diff, where it's the difference between those sprint times, and then I'm going to check, is that normally distributed, and then run the Shapiro-Wilk test on that variable. So I'm going to copy and paste that code here. And then I'll go ahead and run my code as well. So again, we have a small-ish sample size, and so maybe the histogram is not the best way to determine whether our data are normally distributed. So I'm also going to run the Shapiro-Wilk test. And then remember, our null hypothesis is that the data are normally distributed. And our p-value is 0.3864. So it's greater than 0.05. So I fail to reject the null hypothesis. So I accept it and say the data are normally distributed. So the t-test in this case is appropriate. In the exercise, it does say that you need to reshape the data. That is true if you use, I think it's the 2-sample t-test function, but we can actually use the t.test function to run it, and it is okay if our data are wide. So we don't need to restructure our data, which is great. I sort of, so far and maybe all of you are sort of finding too, it's pretty onerous to reshape and restructure and recode our data in R. So if we can avoid it, that's great. We won't always be able to. That is kind of the bulk of our work when we're preparing our data set for analysis. But if we can avoid it, that's great. So, maybe it's setting up our Excel database with our data in a way that we know R is going to need it to be. If we can do some of that work up front, that will save us some time when we actually pull the data into R. So, but thank goodness, in this instance, there is a function that we can use that doesn't require us to reshape our data. So all we need to do is we're going to create this object, and I'm just calling it test1. And then I'm going to run the t.test function. The first variable, so this is the key here, the first variable that I list is going to be the post-supplement sprint time. So I'm going to look, I'll actually show you it both ways. The result is the same, but the resulting mean value is incorrect. So the key here, again, is just to put that second variable, that second time point first, and then that first sprint time as the second variable. And then we put in this argument that paired is equal to true. And then we're just saying here, we want the two-sided test. Okay, so the null hypothesis is there's no difference. So that difference in means equals 0. So let me copy and paste that for you guys. And then I'm going to run that test. Okay, awesome. So we have our t statistic. We have our our p-value is less than 0.05. So remember, our null hypothesis is that there's no difference in the mean. So the difference is equal, the mean of the differences is equal to 0. And our p-value is less than 0.05. So what would we conclude in this instance? And this is the first significant p-value that we've had so far. So it's less than 0.05. So we actually, in this case, we reject the null hypothesis. So we reject the null hypothesis that the mean differences is equal to 0, and in favor of the alternative, which is that the difference in means is not equal to 0. So in this case, this is great. It looks like at least we have statistical evidence that the supplement is effective, and in this case, in decreasing the sprint time. So you see the mean of the differences is negative, which makes sense, right? When we looked at the mean sprint times, pre and post, the sprint times decreased, right? So the mean of the differences, we expect it to be negative. So when I said it wouldn't matter if we ran this with the pre first, let me just show you what that looks like. And then post second, the statistical result is the same. So we still get the same p-value. We have our t statistic, the actual value is the same. It's just one is negative and one is positive, right? So we see a negative up here, but it's positive in this case. The p-value is the same, so we'd actually still come to the same conclusion, but the mean of the differences is in the wrong direction, okay? So it wouldn't be like a horrible error, but it would be more appropriate to put the second time point first and then the initial time point second when we run our t-tests in this way, using this function. And then I think, oh yes, okay. So one last note, and then again, I apologize that I have to log off before, by 10:30. So I'm just going to quickly go over this. Cool fact, the paired t-test is actually just a one sample t-test of the differences. So remember, our one sample t-test tested that our population mean, or I'm sorry, our sample mean is equal to some true value, some population mean. And that's basically what our paired sample t-test is doing, right? It's saying that the mean of the differences is equal to some value, and in this case, that value is 0. So we can actually run a one sample t-test and set our population mean to 0 and get the same result. And so, like, I don't recommend doing this, but I kind of wanted to tie in our one sample t-test and how that ties in with our paired sample t-test. So you see the same result. Our t statistic is the same, our p-value is the same, and then our, the mean is the same, right? Because that's the mean of the differences, and our conclusion would be the same based on those results. So this actually concludes exercise 1. So what I'm going to do is I will post my R code to Cougar Courses so that you guys can use it. You can modify it however you need to in order to run the analysis on your data. And then the exercise will just ask you a few questions. So you might need to not only copy and paste the results that you get from these statistical tests or running the histograms or Shapiro-Wilk test, but also do a little bit of write-up as well. So, for example, you might write up, okay, our p-value is less than 0.05, so we would reject the null hypothesis and conclude that there is a difference pre and post supplement in our sprint times. So that would be an example of what you would need to write up in your exercise. So since we got through exercise 1, what I'll do is ask that you turn in the assignment by next Tuesday. So, and I hate like super hard deadlines. So I don't want to say like 11:59 on Monday, but just, sometime before our lecture on Tuesday. So, even if it's like Tuesday morning, that's fine. And then again, I'm not going to grade these. It's really more to make sure that you're absorbing all of these concepts so that you can apply them in your own research. And then if you're having any issues with code, feel free to reach out to me. My CSUSM email does work now, so I can access it. But I can also, if you're really, really stuck and don't have time to, to reach out to me, I can go through your exercise as well and point out where, something might be going wrong in your code. So the idea, so the idea really is to just make sure that you're picking up these concepts and that you're using, appropriate-ish code in R. And hopefully for this first exercise, you won't have any issues with the code because you have all of the example code that you need. But in future exercises, when I start to sort of like pull back a little and sort of nudge you to write the code yourself, in those cases, again, the coding isn't going to be graded. It really is, I'm really just here to help you so that you'll have the tools that you need. So, okay, so again, Peter, just email me your data set if you haven't already, and I'll take a look at that separately and then email you back and kind of figure out, what may have gone wrong, just so that you're well positioned to, for the remainder of the exercise. Okay, so I'm going to stop recording.